Geometry class, here we go. Section 5-6. I believe this is the last section we're going to officially cover in detail out of Chapter 5. And then we'll have a few more little sections to cover out of Chapter 7 to wrap it up as one official unit. Proving quadrilateral is a parallelogram. So in the last section that we did, they're going to tell you it's a parallelogram or a square or a kite or a rhombus. And then we apply those properties. Today, we can see that it's a four-sided figure. But how do we prove it's a parallelogram? And the way to actually know it, there's 5 different ways to do it. This is kind of like when we had to prove that triangles were congruent. In order to prove triangles congruent, we didn't have to show all 3 angles are congruent to all 3 angles in the other triangle, or we didn't have to prove 3 sides of one triangle congruent to 3 sides. We didn't need all 6 of those. We needed combinations to make angle side angle, or side side side, or angle side, HL. We had those little ways to prove congruent triangles. There are 5 ways that you can show that it's not just a four-sided figure, but it's actually a parallelogram. And I'll put these down and I'll try to highlight the ones that get used more often than not. So obviously the number one way that you can prove something's a parallelogram is if quadrilateral has both, underline both pairs of opposite sides, no comma here, opposite sides parallel, then quad is a parallelogram. Okay? If it has both pairs of opposite sides parallel. So it's important that it's both pairs, because if you only show one pair, let's say the top and the bottom, then it's only a trapezoid. All right, we have to show that the top is parallel to the bottom. There's probably going to be extra lines in there to do that. And this side is parallel to this side. So if that happens, then it's going to be a parallelogram. Number 2, the number 2 way, if both pairs of opposite sides of quadrilateral are congruent, then quadrilateral is officially a parallelogram. So this one, excuse me, this one we don't have to prove parallel lines at all. If we can just somehow do a proof and we can show that the left is congruent to the right and the top is congruent to the bottom, if we can show that, then I could say, hey, it's a parallelogram, because if both pairs of opposite sides, underline both again, both pairs of opposite sides of the quadrilateral are congruent, then the quadrilateral is a parallelogram. This one gets used probably the most, to be honest. This is basically what a parallelogram's definition is, but this one probably gets used more often. I could see them drawing a diagonal in there, and you got to prove this triangle congruent to this triangle. Then by CP/CTC, you get opposite sides congruent. So this one probably gets used the most out of all of them. All right, problem number 3. If both pairs, underline both, if both pairs of opposite angles are congruent. So again, not dealing with parallel lines again, just congruent parts. If both pairs of opposite angles are congruent, then my quadrilateral is officially a parallelogram. And so in that kind of a picture, I have to prove this corner is congruent to that corner, and I have to prove this corner is congruent to that corner. And again, probably using, how do I phrase it? Probably using congruent triangles and CP/CTC and stuff like that. Those 3 definitely get used the most. All right, they get used the most. And then the next one that gets used a little bit tougher, but it does show up. This is if one pair. If one pair of opposite sides are congruent and parallel. They have to be congruent and parallel. I probably should do that. That equal sign looks a little goofy. Let's do it like this. Congruent and parallel. Then the quadrilateral is a parallelogram. So that could be like the top and the bottom, or it could be the left and the right. Let me focus this again. Looks out of focus. There's better. It would look something like, let's do left and right here. You prove these are congruent, and then you prove that the same ones are parallel. It would not work. It would not work if I were to prove these congruent and these parallel. That's a big no. That's actually what an isosceles trapezoid has, those marks. Okay, it has to be the same. It has to be the same pair of opposite sides that are congruent and parallel at the same time. So it can't be these are parallel and these are congruent. That wouldn't work. All right, it has to be that kind of combination of marks on it. And the fifth and final way, probably the least used, and when it is used, it's very obvious. If the diagonals of a quadrilateral, now keep in mind that in a regular parallelogram, the diagonals are not congruent unless it's a rectangle and unless it's a square. But if the diagonals of a quadrilateral bisect each other, all right, if you have a four-sided figure and you draw both diagonals in and they cut each other in half, then it's a parallelogram. So you would have parallelogram shape. One diagonal will be drawn in, and then the other diagonal. This ends up being the midpoint. This is congruent to this. This is congruent to this, but not necessarily all four congruent. I just need one diagonal to be split into two equal pieces, and then the other diagonal split into two congruent segments. All right, now, having done all that, time for an example. This is kind of a proof-heavy section. We won't go crazy with the proofs. Similar to what we did with the last homework, we didn't go crazy on it. Given AFCE is a parallelogram, angle EAD is congruent to angle BCF. I apologize, I probably should have drawn it first. And I need to prove that ABCD is a parallelogram. The picture looks like this. It's going to be a parallelogram here. And then there's going to be one shape kind of inside it. So A, B, F, E, D, and C. So AFCE, the whole thing, is a parallelogram. An angle EAD here is congruent to BCF here. And I got to prove the middle part is a parallelogram. And I got to be honest, there's a lot of ways we can do this proof. It'll be interesting once I do it with you guys in class. You can come up with maybe 3 different ways of doing this. So it all depends on what parts you get congruent, but it probably does rely on congruent triangles. Let me get my 3 steps in there. So AFCE is a parallelogram. That's step 1. Given. Step 2, angle EAD congruent to angle BCF. That's a given. And, well, actually, it's only 2 givens. I thought it was 3 givens. So the whole thing's a parallelogram. So I got to learn how to use this to help me make congruent triangles. Let's see here. How can we do this? If I make congruent triangles, then I can do opposite sides congruent, or I might work with the angles here, get those congruent. That might work better here. All right, what I'm going to do is, since the whole thing is a parallelogram to begin with, I'm going to say that angle EAB is congruent to angle ECF. And I'm going to say opposite angles, not sides, angles of parallelogram are congruent. Now what that does is it makes overlapping congruent angles. Then I'm going to say that angle DAB is congruent to angle DCB by subtraction property. So I'm going to go for opposite angles congruent here. I am still going to need the triangles congruent, so I'm going to say AD is congruent to BC. I'm sorry, I shouldn't do AD. This isn't a parallelogram. Let's go AE. That's better. AE is congruent to FC. Sorry about that. I'm looking at the wrong shape. AE is congruent to FC. And I can put opposite sides of parallelogram congruent. I got an angle, and I can go angle E congruent to angle F. You guys probably saw that earlier than I did. Opposite angles of parallelogram congruent. Now the triangles can be proven congruent. Triangle AED is congruent to triangle AED CFB by angle side angle. So a pair of angles that was given 2, pair of sides 5, other pair of angles 6. For CPCTC, I'm going to say angle EDA is congruent to angle FBC CPCTC. A lot of marks on this picture. Then I could say angle ADC congruent to angle ABC. Sups of congruent angles are congruent. We got like every angle in the picture congruent now. So what I did is I proved these congruent in the triangles, and then I did the supplements congruent. Now I can end it. I got to turn it sideways though. I could say that, let's see the picture, ABCD or I should do it this way. ABCD is parallelogram. And I'm going to use one of my 5 reasons, and I proved angles. I think I could have done sides. I could have done subtraction and sides. That actually might have been easier. Let's see if you guys do that in class. But I'm going to say if both pairs opposite angles congruent, then it's a parallelogram. And that's using the new rule. And I was able to squeeze it in under 15 minutes. Short lesson. Important stuff, though. Pretty important stuff. I think the easier way would have been to prove AF is congruent to EC and do subtraction property here instead of subtraction property of the angles. Get AB congruent to DC and then get these segments congruent by CPCTC. That probably would have been the easier way to do it and do both pairs of opposite sides congruent. I could have done congruent and parallel as well for one pair of sides. Anyway, that's going to wrap it up. The first 3 methods would have worked here. No, heck, the first 4 methods I could have done here. I probably couldn't do parallel lines. I probably could have done method 2, method 3, method 4. Method 1 would have been a little tough. Oh, I got to end it. If you have any questions, let me know.